in this lesson, we're going to look at collisions and momentum conservation, and we're going to return to that two-body system approach. And we're mostly interested in comparing the velocity and momentum before the collision to the velocity and momentum after the collision. Now, in the two-body system approach, we only have internal forces. So we have the force on 1 by 2 and the force on 2 by 1. All external forces, we are going to assume, and it's a very good assumption, very good approximation, are negligible during the actual collision. The collision happens so fast that even if friction or gravity or something is going to affect the velocity after the collision, so now the final velocity of the collision becomes the initial velocity for the external force, gravity or friction, to affect the particles and slow them down or speed them up. But during the actual collision itself, that millisecond or less than a millisecond, we are assuming those external forces will not affect conservation of momentum because we are going to say those external forces are zero. And therefore, the initial momentum of the particles prior to the collision will equal the final momentum of the particles after the collision, and by before and after, I mean just the instant before and instant after. So P initial is only for the instant before the collision, and P final is only for the instant after the collision. And as I said, once we have the velocities after the collision, now we can let external forces affect the motion, but not during the collision. All right, well, we have two categories of collision, as we show down here. We have elastic and inelastic. Well, the most important thing about both elastic and inelastic collisions is the word collision. They are collisions. So P initial equals P final. P initial equals P final regardless of whether it is an elastic, the world's best collision. All of the kinetic energy that was present before the collision was present in the movement of the particles the instant after the collision. Kinetic energy initial equals kinetic energy final. Or whether it's a more realistic real-world collision where we have an inelastic collision and the final kinetic energy will not be what the initial kinetic energy was because there's going to be loss of energy to heat, light, sound, damaged material, all of those observables of a collision. Well, I think the best way to understand what we're going to be doing with collisions and elastic and inelastic calculations will be to do an actual calculation. So here we have an example problem where, what if we're not told whether it's an elastic or inelastic collision? How do we know? Well, you don't initially. What you have to do is calculate the initial kinetic energy, the final kinetic energy, and see whether they equal each other. In this problem, we have two particles, a 5 kilogram particle and a 2 kilogram particle that will be part of the collision. The 2 kilogram particle, as we can see here, is at rest, and the 5 kilogram particle moving at 6 meters per second, so we have a pink initial momentum vector only in the x direction, and it has positive 30, what I am going to refer to as momentum units. So it's technically kilograms meters per second, but 6 times 5 is 30, so we have positive 30 x hat is the initial momentum. That is important. That is so important. Why? Well, because P initial equals P final. So even after the collision, after the 2 kilogram mass scatters upwards and has a, we are told, has a speed of 10 and is scattered at an angle of 30, and we're not told anything about the 5 kilogram mass, just that we know it'll scatter down, but we have to calculate the speed and the angle. Well, what we do know is we had 30 momentum units to the right before the collision. Well, we better have 30 momentum units to the right after the collision. And what we can do is take our 2 kilogram mass here, and we can calculate how much momentum it has in the x direction. So when we do 10, because mv, the momentum is 10, times cosine of 30, we get 8.66 units of momentum to the right. Well, we started with 30, and the 2 kilogram object gave us 8.66, so that means we know, I have the calculation shown down here, that the 5 kilogram mass has to have 21.34 momentum units, or kilograms meters per second. And now we do the same thing in the y direction. And yes, if momentum is conserved, please get this into your notes, if momentum is conserved, it is conserved in both the x and y directions. And in the y direction, we had no initial momentum. So that means we better have no momentum final in the y direction for momentum to be conserved. When we do our 10 sine 30 here, we get 5, so we have 5 momentum units up, which means we better have 5 momentum units down to give us no final momentum because we had no initial momentum. Well, now the problem is really solved. We really have just a little bit of calculation to do, and it's solved because we now know the angle theta, right? We had our pink 21.34 momentum to the right. We had our purple 5 momentum down, so that makes all of the momentum of the 5 kilogram mass. So we do inverse tangent to get 13.2 degrees. We now also know the speed of the particle because we can use the Pythagorean theorem to get the total momentum, 21.29. We know it's a 5 kilogram mass, so we can get the speed of the 5 kilogram object after the collision. And now we simply calculate the kinetic energy before the collision, the kinetic energy after the collision. We take a look at the difference between the two, and by the way, they're not equal, right? We start with 90 joules, 1/2 mv squared. We do 1/2 mv squared for both of the particles after the collision. We only get 73.04. So it is definitely inelastic, and we can calculate just doing our basic percent difference between the two. So if we recovered all of it, we would have had 90, so it's kind of like the theoretically perfect minus the actual divided by the theoretically perfect times 100 gives us 18.8% of the initial energy was lost. And the only thing we have to be a little careful with is when we classify our collisions as elastic and inelastic, that there certainly will be some gray area. What do I mean by some gray area? Well, what if instead of kinetic energy final being 73.04, it had been 89.9? So technically, 89.9 is not 90, it's inelastic. But that's pretty darn elastic. It's nearly elastic. So what we use is like a kind of a 5% rule as a ballpark, though there is no convention that it has to be so, to say that if it's within 5% energy loss, so in other words, you've recovered 95% of the initial kinetic energy. So in this case, it would be roughly 86 joules. So had the final kinetic energy been actually 86 joules, so we would have recovered 95% of our initial kinetic energy, we would say technically it's inelastic, but it's nearly elastic. This is not a bad collision in terms of elasticity. So there we have our basics for elastic, inelastic collisions. and we will be using this to help us problem solve problems, a very powerful technique.